Okay, just to repeat while you all think, we got a simple harmonic oscillator. Its total energy is E, that's with respect to the equilibrium position. It's got a mass M and an amplitude A. That's all we know about it. We want to find the equation of motion. So how are we going to do that? We're going to discuss that for a minute. Okay, now I've chosen this situation intentionally, because I think most people are going to have trouble with it, not know where to go. Okay, so we just talked for a while about, where do you go with this stuff? So people are talking about things like, people are drawing free body diagrams that look like this. Which is totally relevant. If this thing happens to be a pendulum, that's a good free body diagram for pendulum. Okay, that's really good. Okay, I'm really happy to see that. This thing's choking me. Have to wear it outside. So, on the temperature's over 40 degrees. But it's nice and warm. I kind of recommend it if your face gets cold. Okay. Okay. Simple harmonic oscillator. Okay. So that was one idea that I saw. And there were a lot of good ideas that came out. Okay. And then somebody said something about, well, amplitude, potential energy, equal and opposite to the work done by the conservative force. Okay. That was really good. Okay. So, I'm abbreviating it here because I don't want to have to write out the whole phrase, but you need to know that whole phrase, and I'm glad I heard it. Okay. So there's a lot of good stuff, and people are thinking conceptually, but they're missing the essential relationships. Okay. Now we finally did get to somebody said, because the thing I wanted you to focus on is, okay, in terms of what you were talking about, what is restoring force? Okay. And nobody knew. It's fundamental. It's where you start. It's where you get the differential equation that leads to the formula for the equation of motion. Okay. If you don't know that, and if you haven't put that together with the differential equations course that everybody's taken or has taken, kind of missing a connection that could be really helpful to you. They're not required to be able to solve that equation, but you are required to be able to prove that the solution is what it is. Okay. But again, if you were asked to solve that equation, it would be the easiest problem when your differential equation is final. Okay. It's really a calculus 1 question. All right. So it's something I really kind of advocate that Okay, well, again, here we are. We still aren't making a whole lot of progress because we aren't sure what some of the relationships are. Now, somebody said something about -1/2 kx. You're getting more. Okay. But, you make yourself a note that the net force is -kx. And you can write out this. Okay. And that embodies what everybody was wanting to say. If you let x1 equal 0 and let x2 equal x, which would be clumsy because we're integrating with respect to x. So you just let x2 equal x at this point, you get 1/2 kx squared. There's your potential energy function for your simple harmonic oscillator, okay? Now that's stuff that everybody was on the verge of pulling out of their memory, and next week is the final, and you don't want to have to be on the verge. Okay, I'm not going to give you all these formulas. You need to know them because they're fundamental to understanding. Y is F net equal to negative kx. It's a linear force, so it's a multiple of x. Okay, and it's proportional to how far you are from equilibrium. There's your proportionality constant k, and it's back toward x equals 0, so you have the negative. And right there's the restoring force for a pendulum of low amplitude. And the details of that, well, you should be able to do that, okay? Okay, now still, okay. Does any of this apply directly to any of this? Well, it doesn't because you don't know what K is, right? If you knew what K was, you could say a whole lot because you know the amplitudes and then you know the potential energy at the amplitude. But I did give you the total energy. Okay. Now, what is the total energy? And I maybe say total mechanical energy. Letters. Okay, what's a total mechanical energy? What's the definition of total mechanical energy? Okay, now when I posed that question, I got a good answer with a couple of looks like coming, it's coming. Okay, a little dubious, but you've heard the term, and it should lock in since you just heard it. Okay, and it wasn't from me. It's the total mechanical energy is the sum of the potential and kinetic energies. So, okay. The clue is pretty much so what can we find from the given information? And is there anything else we might want to think of? Well, let me just make note, this other thing that we might want to think of is equation of motion. Anybody tell me what the equation of motion is? Okay, now I heard, this is the one I usually use. E to the I omega t is more general. Cosine omega t plus I sine omega t, where the coefficients of the two things can be complex. We combine them into sines and cosines. So it's worth thinking about. And it's also, I think, probably worth understanding your differential equations course. Now, as I said, you don't have to know the differential equations, but I'm mentioning this because almost everybody in here is taking it or has taken it. I think everybody is taking it or has taken it. Okay. And it can be handy. It can help you with the physics, which is the only reason I mentioned it. Your choice, whether you want to think about that or not. If you know this, that's really kind of sufficient. You really ought to be able to combine cosines and sines with different amplitudes to get the final amplitude and stuff like that. because that's just basic trigonometry. But I'm not going to ask you to do that, okay? Just giving you context. So we have this equation, and this could be a sine. Of course, you just let pi equal 2 pi, okay? Or negative 2 pi. Then you have the sine function, right? But you can let phi equal anything. And for most applications, for this particular question, you don't need to know pi, so you can just let phi equal 0. Or negative 2 pi, or just use the sine. Any linear combination of sine and cosine would do. Okay, that's again just context. Now, get down to the specifics. What can we find from the general information? And notice that the equation of motion is what we want to find. So maybe we write this one down off to the side someplace before we start trying to put stuff together, right? Okay, well, you have now simple harmonic motion. You know the amplitude, and you know what? Total mechanical energy, right? So what can you say about the energy state when x is equal to the amplitude? In other words, out there where the thing is at its maximum displacement from equilibrium, what can you say about the energy? Okay, so the question was, what do you know about the energy state when you're at maximum displacement? When you're, when the thing comes to rest for an instant or it swings back or gets pulled back. And somebody said, the energy is equal to the potential energy. Total energy is potential energy. Well, why is that? Because it ain't moving. Or something similar to that, right? Velocity is 0. Okay. So since this is the sum of kinetic and potential energy, we can say to get the insight, we'll put a subscript here to remind us that this is the total mechanical energy. That's just taught. Okay. TO2. So potential energy is the total energy. Well, now we know the potential energy at the extreme position, right? Okay. Well, if we know the potential energy at the extreme position, what else do we know about the potential energy? Here's the key. Okay, you say, I'm asking, what's a potential energy? What's a potential energy out there? At any position, give me some relationship with potential energy. Nobody seems to want to do it, even though it's right here. Okay, we just talked about it, and you should lock that in because somebody almost said it half an hour ago. All right, yeah, I know. What I used to do with one of my best students of all, well, circling the board, put your forehead in it. Okay. It's one of those, or okay. Let's get rid of my head. Okay. And I got my grandson doing that a lot too. Okay. So one of the people that did that is a PhD mathematician working high level for Google. Okay. Uh, there's in his second year as an electrical engineer, seems to be doing really well. Okay, so anyhow, you might think of that. Here we get to my main theme, if there is one. Okay. That's a key insight. Drill it into your head and use it. If you use it a few times, you'll remember it. But again, you got to do some problems and analyze and understand in order to put the pieces together. It's like a jigsaw puzzle. First time you put it together, it's really hard. Second time it gets a little easier, although jigsaw puzzles never get quite as easy as this does. Okay. Now, what can you determine from this insight and this key insight? It's really kind of a focal point when you're talking about simple harmonic motion. Okay, now I hear people saying things like, well, they solved the equation in their head, it looks like, okay? And it sounds kind of reasonable, but not saying it quite loud enough that I can hear everything. And even if I could, I'm going to pretend I didn't, because I don't want to skip to the solution of the equation until we have an equation or relationship. Okay, what do we have here? You know, between this and this, what do we know? Well, don't we have two expressions for the potential energy? One of which is something we're given. Okay. So okay. I should have written this first. X equals A. And it could be plus or minus A. It's the same both places, so I'll put a plus or minus in there that nobody's going to be able to read. But it's worth kind of noting. Doesn't matter if you're plus A or minus A, because A is going to be squared. You're going to get the same thing either way, right? And your potential energy is E total either way, because this expression here involves only X squared, right? So it's always going to be positive or zero. It's never going to be negative. Okay. So we know the potential energy is E total, potential energy is 1/2 Ka squared. What are we given? We're given E total and we're given A. Ain't that neat? Well, that means we can set this equal to this and solve for K, can't we? Okay. So we solved the equation for K, not A. I wrote down A. Probably just because my eye called an A there. But there it is. Okay. So if we're given total energy in A, we can find K. All right. Is that going to help us find the equation of motion? What do we need for the equation of motion that we don't have? One thing we need is omega, because I haven't been specific about the initial condition. Okay, I just said find equation of motion. So any equation of motion will do at this point. Well, we can still keep phi in our equation. Understanding we set phi equal to anything is not going to make any difference. Okay. So now we've penetrated the mystery somewhat, because knowing total energy and amplitude tells us, okay, for simple harmonic motion. Okay. Now, one thing I've heard a lot of in our discussions is things about gravity, mgy or mg double y or mgh or whatever. Okay. And that's all relevant if you have a pendulum, because you can analyze a pendulum based on potential energy due to gravity. Okay. But it's a little more complicated because you got to have that arc of a circle and you got to do a little Pythagorean theorem and stuff like that. We've done it. It's not hard. Okay. And in small energy or in small displacement approximation, you know that K is mg over L. And if you don't, learn to prove it by that diagram, because I might well ask you to do so. Okay. So this thing, incidentally, implies a pendulum with A much less than L. Okay, and you should know what those symbols mean, symbols we used when we analyzed in the first place. This isn't a pendulum. It might be a pendulum, but you can't assume it's a pendulum, and you don't want to analyze it as if it's a pendulum, because then you start getting a pretty complicated relationship about potential energies. Okay, it's a simple harmonic oscillator, and if it's a simple harmonic oscillator, it's this. That force is negative kx. That's it. If it's not equal to negative kx, it's not a simple harmonic oscillator. It might be close to simple harmonic, okay, but it's not simple harmonic. All right. So we have an expression for k. So now we know k. That's a big deal. We've actually found something. What else do we need to know in order to write the equation? We have A. Again, we need omega. I don't know what you're going to do about omega. Well, let's do what a lot of you have wanted to do. You keep wanting to go back to the equilibrium position and find the kinetic energy, right? Okay, well, that's fine. That's actually what we need to do. Okay. So as I said, when you said it, I said, yeah, but we're going to stick with this rather than confusing it with that, because we know what to do with that. Okay. And people have already said it. Now, when x equals 0, kinetic energy is equal to total energy, since the potential energy is calculated from 0, right? Now, you want to be careful that the potential energy is being calculated from the equilibrium position, which is what you always want to do with simple harmonic motion. Okay. And I said here, with respect to equilibrium. So I'm specific about that. Sometimes I leave stuff like that off. In a case like this, you could assume it's implicit, okay? But I should write it out just to make sure that everything is declared in the statement of the problem, okay? But it's something that should be implicit is not explicitly addressed. You're free to make a judgment. Of course, if you're wrong, you fail. No, you're free to make a judgment and make reasonable assumptions, right? Okay, so anyhow, back to this. X equals 0, we get this. So 1/2 m v max squared equals E total. Okay. But E total is also 1/2 KA squared. Thus 1/2 m v max squared equals 1/2 KA squared. So that V max squared over A squared will equal K over M, 1/2 can you multiply everything by 2 and all that stuff. And that actually comes out V max equals A times the square root of K over M. Okay. That makes sense. Now, what's the big deal about the square root of K over M? Okay, so somebody identified this as omega, right? And you're right. Why is that omega? And let's just go back to the differential equation. Mass times acceleration is negative kx. Acceleration's x double prime. So x double prime equals negative k over m times x. It's great if you think about that and understand this connection, because you'll not only know that the square root of k over m is what I mean by omega. Okay. But you know why. And then you relate this to the circular motion, angular velocity. That equals omega t. And right down here is your cosine. And if this thing has radius A, it's A times the cosine of omega t. And when t equals 0, if you want phi to equal something besides 0, then you add the phi in there. Okay. So for many reasons, you really want to try to understand this picture, especially since it relates to circular motion, which we've talked a lot about and demonstrated. The primary thing we've used in lab is this rotating beam, okay? Makes it fairly easy to visualize this in a tangible way. It's well worth doing. Now, I don't have time to do everything between now and the final. If you can do that with 10 minutes of thinking, it's probably worth it. If it's going to take you hours, don't bother. Just remember the formulas, okay? Make your own judgment. Okay, well, how does that help us here? We know that omega is the square root of k over m. Well, I guess we've just determined omega, haven't we? We really didn't even need this. If we knew right off the bat that omega is the square root of k over m, because what else did I give you? I gave you m, we just found k, right? But we analyzed this, and that's kind of an important relationship, okay? If the total energy occurs at the equilibrium position, so the potential energy is zero, so total energy at that point is equal to the kinetic energy. Okay. And at this point, because there, the thing is temporarily stopped. There's your kinetic energy, right? All potential. Okay. You want to have that whole perspective. Because that can really be helpful in understanding how everything fits together with some harmonic motion. All right. Well, what do we do now? It's like we've got the equation of motion. Now, there are consistency. Okay, so, okay. I'll write this in function form, x of t equals a cosine omega t. And keep pi there, take it along for the ride. And if there's no reason to have it equal anything but zero, let it equal zero. And then you have this picture with the cosine oscillating back and forth between here and there. Okay. If you want to use the sine, well, get up and down or well, you take the derivative of that and you get the velocity, right? Okay. What's the maximum velocity? Okay, we got a question. We've established that the maximum of v of t is going to occur when the sine of omega t is either 1 or -1, because those are the extreme values of the sine. Since you have a negative out here, well, when the sine is -1, but that tells you that the maximum is omega a. We already said here that the maximum is a times what we've identified as omega, right? Not pretty small. I don't know if that's going to be legible. Yeah, I just said that this is omega a, where omega is the square root of k over m. The k square root of k over m comes out of this differential equation. You just use your trial solution, e to the I omega t, okay? Or e to the I RT, whatever you want. And plug it in here and get your characteristic equation, solve that characteristic equation for r, and you're going to get square root of k over m. Because you're going to get r squared when you take two derivatives. of e to the IRT, right? That's your differential equations. And I hope that helps you with your differential equations, as well as maybe helping clarify what this is. Because I think it's probably some necessary part of solving a higher order differential equation. That's where you start. Okay, just for perspective. Now back to this. So we've got kind of full circle between the equations and what we got without using any equations, right? Which should be convincing that the equation is good. Again, why is omega the square root of k over m? It's because you're going to get an r squared equals k over m in your characteristic equation, okay? But that involves differential equations, which we officially can't assume in this course. And I wouldn't be talking that much about it if everybody wasn't also taking or has taken it. Okay? So that's it. The other reason it's got to be the square root of k over m is if it isn't the square root of k over m, you plug it in to here with this relationship, and you get a k squared over m squared instead of k over m, where you should be getting a k over m. In other words, the second derivative of this thing doesn't give you k over negative k over m. It gives you negative k squared over m squared if omega was k over m. So it's got to be square root of k over m to fit this. And that's all I've asked you to do on the transition problems that I gave you, is verify this for a bunch of different forms. So that shouldn't be a question at this point, because that was a really easy question. All I got to do is be able to take derivatives. Okay. Also, you have the acceleration equals negative omega squared a cosine of omega t plus pi. So among other things, a of t equals negative omega squared x of t. A equals negative k over m x, which is what we have down here. So you can get the energy relationships if you know enough about the equations. You can get the equations if you know enough about the energy relationships, which is my main theme here. If you can pull that picture together, it's a unifying idea that gives you a sufficient level of mastery to do well on simple harmonic motion problems, which students almost never do. Okay. Last year was the first year I finally succeeded in talking about the pivotal nature of this relationship, omega equals square root of k over m. It's pivotal, as are your energy relationships, and especially your potential energy. Make sense? Make sure that comes together, because it's going to be important in the final. Okay. Okay, I got somebody in here who's been totally upset for about the last 30 minutes. With good reason. Notice that I slipped in a little error here to see if you're making good sense out of what I'm telling you. I pretended to make a mistake so you could catch it. Actually, I just plain old wrote that down carelessly. And you've seen me do that many times before. You remember I wrote down A here accidentally and solved that in my head for A. And then I said, no, that's supposed to be K. So K equals 2 B total over A squared, which is then going to be dimensionally consistent. Okay. Because the dimensions didn't work with that square root there. Okay. And I think maybe I I don't remember if I had an a squared in the denominator now or not. I've erased it. It's gone. Posterity will never notice it, but there it is. Okay. Now, is that dimensionally consistent? Well, you just think your dimensions energy is like kilogram meters squared per second squared, right? And if you divide that by meters squared, you get kilograms over second squared, which is like kilogram meters per second squared over meters, which is newtons over meters, force over mass, which is what the units of K are. Okay. K is in newtons per meter. Okay. In SI units. Or you think length and mass and all that stuff. Kind of easier to think in terms of newtons, meters, and seconds, but it's totally equivalent. So you should be able to do it either way, but obviously then, since this works out with SI units, the dimensions are consistent, and the other isn't. And you should always check the dimensions of what you do. I was so busy wanting to get to this, I wrote it down carelessly. Okay. So thank you for the correction. Okay, now. Right there is your total mechanical energy equals the potential energy at your extreme position, right? And that means that your kinetic energy is this minus this. Okay. This can also be written in terms of equations of motion. Substituting negative omega a sine of omega t plus phi for the velocity. And we just put all that down here. Once we know that x can be expressed as a cosine of omega t plus phi, if we use that expression for our position function, then these are the positions for our velocity and acceleration functions. There are many other alternatives for the x of t. The key problem that I had you work out gave you a number of expressions to verify as solutions to the differential equation. Okay. We've chosen this one. We could have chosen a different one, would have given us a different velocity, a different acceleration function. But whatever velocity and acceleration functions follow from the position function that we choose, we can plug them in to this equation. Long careless omega there. Okay. Now, does that work? Can you verify that? Easily verified, since the sine squared or whatever, plus the cosine squared of the same whatever equals 1, right? The Pythagorean identity. Because right here, you have a cosine squared. Right here, you're going to have a sine squared. Then you have your relationships between omega and k and m. I heartily recommend that you verify this and relate it to this. It's good stuff. You can go from the, what I might call the energy domain to the time domain. And they're doing Laplace transforms, aren't you? You know, you go from the differential equation domain to the algebra domain, right? So it's kind of analogous. You have two different domains, two different ways to look at everything. You want to be able to put them together. Okay, that's kind of where the analogy stops. It's not the same stuff by any means, but okay. Now, oh yeah, let me relate this. You know, I wanted to pull this into the whole thing about orbital mechanics and so forth, but we'll do that next time. Okay, because what we're doing is review. This isn't a review where I tell you this is equation, this is equation, this is equation, this is what it means. This is a review in the sense of here's what you need to unify. Okay, or here's one way I think should work to help you unify it. Okay, it's up to you to do the work and pull it together, and of course ask me questions at any time. All right. Um, it also works for rotation. Simple harmonic motion of an extended body. Okay, now I just went back and tweaked one of these rotating beams and it's oscillating back and forth and will be probably until past the end of this class. Because we have pretty good bearings there. Actually, it won't be because there's some friction. It doesn't have a lot of kinetic energy, but it's going to have exactly the same equation, right? What else? What can you tell me about energy? Next line is 1/2 k theta squared, right? Give me something else. Okay, kinetic energy. And you give me this, yeah, I'm getting everything. This is the order in which you all have told me stuff. Okay, it's all good. And that's almost all you need. Okay. But where does it come from? That torque is negative k theta. Okay. Now the units of K are a little different. It's not force anymore. I like to write it meters times newtons. Okay. For radian, because if you multiply newtons, meter newtons per radian times radians, you get meter newtons, which is an expression for torque, right? Okay. Now there's some connections here and we're out of time. This just means that your units are different. I's in kilogram meter squared, omega's in radians per second. Okay. Or reciprocal second squared, so reciprocal seconds. Because radian's kind of a phantom unit that comes in and out. Sometimes, well, won't talk too much about radians. If you want me to explain that next time, I will. Take a little longer than we have right now, but not long. So everything is totally analogous. Differential equation is totally analogous. The expression for kinetic energy and the expression for potential energy, and y'all did well. You know, I mean, I dragged it out of at least one of you, and each one, it wasn't always the same person, which means that there's some, you know, synthesis going on there, right? So I could ask you about the beam, I could ask you about the pendulum, I could ask you about the mass on a spring. Okay. So there it is. Next time we'll talk more about some analogies between how the potential energy is used here and how it manifests itself in orbital mechanics. We talk a little bit about elliptical orbits in a way that brings a lot of stuff together. Okay. You're not going to have to analyze an elliptical orbit, but there are questions that could be asked. So we'll go from there next time.